This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
So we've seen one form of coefficient of correlation. Remember, the coefficient of correlation tells you something about how well associated two variables are. In other words, as one changes, does the other one kind of change in step? The method we saw was called Spearman's coefficient of correlation, and here we have another one. It's called Spearman's rank coefficient of correlation. And this is to do with how two sets of variables line up. So you could have a class of 20 pupils in a school, and they do two exams, one in English, one in mathematics, and you want to see, do the people who do well in English, do they also tend to do well in mathematics? So we could number them 1 to 20 in terms of their performance in each of the two exams, and see how well the people come kind of 1, 2, 3, 4 in one, come 1, 2, 3, 4 in the other, or is there a kind of almost reversal in how well they're correlated? Here's the formula. We have n. N is the number of readings you have, the number of, say, pupils in a class. We're doing it like that. And D is a difference in their rankings. And D squared is that squared. So let's see an example of this. Okay, so here we're not doing it with English and mathematics. We're doing it with two accountancy subjects, an accountancy exam and a law exam. And you see that we have 7 pupils. So the n in here, when we get down to it, is going to be 7. So here we have on the bottom here 7, and then we have n squared, we have 49. And what we have are the two rankings, and you simply subtract one from the other. Doesn't matter which way around, because we go from d to d squared, and that means everything in there is going to be positive. So minus 2 times minus 2 is plus 4. Okay? So if we take the top 2 and the bottom 2 just to show you what's happening, 1 minus 3 is minus 2. Minus 2 squared is 4. 4 minus 7 is minus 3. Minus 3 squared is plus 9. Down here, 7 minus 4 is 3. 3 squared is 9. 6 minus 5 is 1. 1 squared is 1. And what we need here is essentially, this is just here, these d should add up to 0 in here. It's sigma d squared, the sum of d squared. So 4 plus 9 all the way down here is going to give us 26. That's what we need for that part of the formula. So we put it in here, so it's 1 minus 6 times the d squared 26 over 7 times 49 minus 1. It's coming to be like that. And we come out here with the coefficient of correlation. This is the rank coefficient of correlation of 0.536. And that's actually quite small, because if we took r squared here, a kind of coefficient of determination there, 0.536, it's coming to about around 30%, 28%, 29%, something of that sort. And that's saying that the kind of variation in your rankings in one exam is only kind of 30% dependent or related to or associated with your rankings in the other exam, but there's another, it's 29%, there's another 71% somewhere that's caused by other factors. But Spearman's rank coefficient of correlation, nice and easy to work out. I can give quite good insights about how well two different orders are actually going to be related. Now, linear regression, if you remember, gave us the best straight line it could through any set of points, even if they were essentially random points. But we know that some relationships are not going to be linear, and that as time passes, you would expect these let's say sales or costs to kind of go up and down. So if it's costs, if it's heating costs, you expect them to go up and down as you go between summer and winter. If it's sales, you expect them to maybe go up and down depending on the season of the year it is and so on. So it would seem foolish to say, I know that heating costs are not going to be linear with respect to time, but why on earth would I try and force them into some sort of linear relationship? We're dealing here with what's called a time series, and a time series is one which moves with time, like sales per day, or maybe costs per day, or maybe the number of people who come into your shop every week. We could keep track of that. Anything which varies with time is a time series. And there can be 4 components of a time series. First of all, there is a trend, which is the underlying kind of general increase or general decrease as you go through time. Leaving aside all of the other ups and downs, we might see that it's kind of on average increasing or decreasing. That's the trend. And then you have what's called a seasonal variation. And a seasonal variation is a variation which takes place in less than a year. We tend to think of summer, autumn, winter, spring and so on. It doesn't have to be those seasons. It could be days in the week, 5 trading days in a week, Monday through Friday or something. Those would be regarded as seasons as well, if there was some sort of kind of repeating pattern in sales per day through the week. You can have cyclical variations, and if you remember back to one of the very early lectures, we talked about trade cycles, where the whole economy goes through a kind of boom and a bust. Very high activity at one point, and then kind of recession sets in, and we get a trough here, a few years of recession, and then maybe it comes up again. That's really the cyclical variations. And finally, we have random, unpredictable, irregular variations. Something happens politically, say, out of the blue, and suddenly people get frightened and sales kind of drop away for a little while, or something of that sort. Time series analysis says nothing, doesn't try to analyze cyclical variations. Typically these are very long range, something like 12 years. And really the purpose of time series is to try to predict, and you'd be foolish to try to predict over something like 10, 12 years anyhow. It's far too many things will happen that you don't know about. And obviously you can't do very much about random variations. You can't predict random variations, really by definition. So time series analysis concentrates on trying to analyze the trend and analyze the seasonal variations, whether it's days of the week or months of the year or quarters of the year. What we've got here is hopefully you can see it here, is showing a rising trend. So going through time out here. This is maybe sales, doesn't have to be sales, but up there. And the way it's actually going is like that. You see a kind of fairly regular pattern. So maybe this is a summer sales, and maybe this is a winter sales down there, and then we have got the spring and the autumn in here somewhere. And you can see, although it's going up and down like this, it does seem to be increasing here, and that would be the trend. And then superimposed on this trend, you have particularly high in summer, particularly low in winter. And if we're going to be trying to say, well, what are the sales going to be next autumn, then what you would do is you would extrapolate the trend, and then you say, is autumn a high or a low type of season there? And you'd add a little bit on or take a little bit off, depending on what sort of season autumn was or summer was or winter was. And hopefully this will give you a much more accurate prediction about what sales are, or what demand is going to be, or what costs are going to be, whatever the variable is that you're plotting out against time. And the method we use is what's called moving averages. And we'll just talk through this very, very slowly so we see what's kind of happening. So here we have a number of years. Here, year 1, year 2, year 3. And what we have are sales in units for each quarter. So here we have year 1, quarter 1, sales 4,800. And then in quarter 2, 2,200 and so on, like that. Then we start in year 2, quarter 1 again, sales 2,760 and so on. So this is our raw data in here, the sales for each quarter for each of the years. And we've got reason to believe that these 4 quarters, that this performs your kind of seasonal variations, and we come round to quarter 1 again, kind of to where we were. Now the method of moving averages is as follows. The first thing you do is you say, well, I think there's 4 quarters making up my seasonal variations here. What you do first of all is you average out, the first 4. So this one, and that one, and that one, and that one. If you add them up and you divide by 4, you will get that. Okay? So that one there is the average from there down to there, coming out there. And you can see almost physically it's in between seasons 2 and 3. But we have a good season in there and a bad season in there, and we've got the 2 kind of medium seasons in there as well, if we're thinking of, spring, summer, autumn, winter. And then what you do is you move down 1 season. So the next one we're going to be doing is we're going to be taking from there down 1, but we're going to take in 1 at the bottom. So we're going from there to there. And of course we still have 4 seasons in there. We still have spring, summer, autumn, winter in there. And we average that out to be there. And then you move down another one. You move down 1 season each time, always averaging 4 seasons. And this is what's called your 4-part moving average, because each of these figures here has got 4 seasons averaged out in it. Good ones, bad ones, medium ones. The trouble with this is that physically that this figure we have here is kind of in between 2 seasons. It doesn't really line up with any particular season. So what we do is we do it again. So we'll average that one and that one. So you can see if you add those 2 up and divide by 2, because you've got 2 figures to add together then, so we have 2975 plus 2465 divided that by 2, we're going to have 2720. And then we'll average these 2 here, like that, and so on, like that. And the great thing now is with what's known as centered these moving averages, that this figure here, let me just get rid of some of this in here if I can. We've seen how that's happening in there. That this figure here is opposite there, yeah? This figure here is opposite that season and so on, yeah? Now this here is the trend. Because what we've done is we've kind of averaged out or tried to eliminate the seasonal variations, because in these trend figures we have got this mix of good seasons, bad seasons, plus a bit extra, less a bit in the bad seasons. They're going to average out the ups and the downs within the seasons. And that is your trend figure. And then we compare the trend figure to the actual sales in the season. So here we see the trend is 2720. The actual sales figure is 2400. So the actual sales are below the trend. So this looks like a bad season. So here we have minus 320. The next one, we're nearly spot on. The trend figure 2490. The actual sales 2500. It's only 10 adrift. This one looks like a good season. 2760, 2590 It's a positive kind of season. It's a favourable season. It's well up, and then we're well down, and so on. And what we do is that we collect these seasonal variations together and collect them by season. So if we look at the Q1 seasonal variations, the first one we have is in here, 170, and the next one we've actually got is in here, minus 129, and we're going to average them out. 170 minus 129, 41. Season 2, minus 286 plus 381, averages out a bit positive, yeah? And then Q3, these are the best bits of information we have about the seasonal variations. This one here, nearly 0, and then Q4, very small seasonal variation. Now, how are we going to do our predictions? So it says here, if we wanted to predict the sales in Q2, essentially if we want, then, and let's say it's going to be Q2 of year 4. So year 4, Q2. Okay. First thing to do is to find out what is the trend figure. So the trend figure starts here at 2720 and goes up to 2451. So we've made a journey in there of 2451 minus 2720. That's what the trend has increased by. And how many seasons has it gone through to do that? How many little increments are there? Well, there's 1, 2, 3, 4, 5, 6, 7. So there are 7 little jumps, little increments there to get us from 2451 up to 2720. Or as it happens to be here, down. Okay, we're going down in this one here. So 2451, there's no reason why trends have to be positive. Divided by 7, we're coming in at about, let's call it 36, because that's what we've got in here. I think it's actually 38, but let's call it 36. Okay. So it's saying that, as far as we can see, every season we go through, the sales are decreasing by 36. So if we want to get to year 4, Q2, well, if we put in year 4 here, we're going to have Q1, Q2. We're going to be going from this trend figure to here, so there's 1 jump, then from here to here 2 jumps, and from 4 to there 3 jumps, and from there to there 4 jumps. We've got 4 seasons to get through. Okay, so we're going to travel from 2451 through 4 more seasons to get us to year 4, season 2. We're going to be reducing by 36 and 36 and 36 and 36. Okay, so we can take 2451 minus 436. And then we say, but that's just the trend. Is season 2 a high season or a low season? And we see here that season 2 or Q2 is a high season. So we want to adjust or correct for that season there. And our prediction for that quarter is going to be 2403. So it's terribly time consuming. So it is. I think it's pretty unlikely in the exam they'd actually ask you to do a whole question. They couldn't possibly do that in kind of objective test questions. But what they might do is to say, well, the trend figure is 50. The seasonal variations are 30, 20, minus 10, minus 15 or something. and say, right, we want to move you to 5 seasons further on. What is the predicted figure? So if it's 5 seasons further on, you'd be adding on 5 times that, the 50, and then say, well, what season does that land me on? And then you would add or subtract the seasonal variations to get you to the best prediction you can for a very specifically tailored prediction for that particular season.